So far, we have discussed the Dirac equation and the Dirac spinors. So the spinors describe the spin half particles, and there are 4 solutions for the Dirac spinor plane wave, and 2 of them describe the positive energy solution, 2 of them describe negative energy solutions, and the 2 positive states are meant to describe the 2 spin states of the electron. It was already realized at the time that Dirac put up the Dirac equation that in the interactions with the electromagnetic field, the electrons behaved in 2 ways depending on spin, internal spin. Now, to generate the relevant equation for antiparticles, we will now investigate the Hermitian conjugate of the Dirac equation. So, the Dirac equation is written in many ways. One of them is I gamma mu d mu minus m, remembering that the gamma is a 4x4 matrix in spinor space, and so we multiply here by the identity matrix in spinor space, acting on the spinor column vector is equal to 0. That's one way to write the Dirac equation. If we make the usual identification in wave mechanics of d mu going to minus I p mu, or I d mu goes to p mu, that's obtained by Fourier transforming a plane wave, then the Dirac equation can also be written as I d slash minus m. Sorry, that's not using the identification, that's just using the Dirac notation of slash meaning contraction with the gamma matrix, but using this wave mechanics identification, we can write this as p slash minus m acting on the spinor is equal to 0. That's the Dirac equation for the spinors. Now, in order to get the Dirac equation for antiparticles, let's try what happens with the Hermitian conjugate of the Dirac equation. Now, for the Hermitian conjugate, we have to remember that gamma I Hermitian conjugated is minus gamma I. Hermitian conjugate means transposed and complex conjugated. When you do that on the gamma 1, 2, 3, it's equivalent to changing sign. For gamma 0, it's invariant under Hermitian conjugation. Therefore, if we start from the Dirac equation, I gamma mu d mu minus m, let's leave out the spinor notation, psi, and we do conjugation, we get, this is all a number, it's equal to 0, so if we conjugate it, then we start by we start reading it from the right hand side, and we get psi bar minus I gamma mu Hermitian conjugated d mu minus m is equal to 0. Right? So, because of the behavior of the gamma matrices under Hermitian conjugation, this is equal, this means that we have psi dagger, then we just write out the contraction with the mu here. We have minus I gamma 0 d0, and then because gamma 1, 2, 3 change sign under Hermitian conjugation, we get a plus I gamma I di minus m is equal to 0. Now, this may not look relativistically covariant because that the gamma naught and the gamma 1, 2, 3, the contraction here, enter with different signs. So this equation, as written here, does not look covariant. It is covariant. In order to show that, or it can be put on a covariant form, in order to show that, we multiply from the right with gamma 0, and we use the identities that the anti-commutator gamma 0, gamma I is equal to 0. They all come from gamma 0, gamma mu, gamma nu is 2g mu nu. So if you have a gamma 0 with a gamma I, you get 0. So gamma mu, gamma nu is 2g mu nu. Gamma 0, gamma I is 0, the anti-commutator. So that means that gamma 0, gamma I is equal to minus gamma I, gamma 0. So if you multiply this equation here from the right with a gamma 0, then that becomes psi bar, psi dagger, minus I gamma 0 d0 plus I gamma I di minus m multiplied by gamma 0 from the right. Now gamma 0 doesn't depend on the position or the momentum, so it commutes through the derivatives. It commutes through the derivatives, but if we want to move it, gamma 0, all the way to the left, it has to commute through the gamma I. When it commutes through the gamma I, it changes sign on the product. Of course, it commutes with gamma 0 itself. So this is psi dagger. If we commute the gamma 0 all the way to the left, we get gamma 0. Here we get minus I gamma 0 d0. There's a change of sign from commuting the gamma 0 through here. Gamma I di minus m is equal to 0. Now we have the same sign on the gamma 0 contraction and the gamma 1, 2, 3. So therefore, we can write this as psi dagger gamma 0 minus I gamma mu d mu minus m is equal to 0. So we see that it is indeed relativistically covariant. And that's true when it's obvious when it acts on psi dagger gamma 0. It wasn't clear when it was acting just on psi dagger. So if we define psi bar as psi dagger gamma 0, then we can write this equation as psi bar I gamma mu d mu plus m is equal to 0. So if our psi solves the normal Dirac equation, then our psi bar will solve the Dirac equation for the antiparticle, which says that psi bar p slash plus m is equal to 0. So psi bar solves a Dirac equation that says p slash plus m equal to 0, whereas psi solves a Dirac equation that says p slash minus m acting on psi is equal to 0. The difference is the sign on the term m. And of course that implies a change in the energy level also at p equals 0. I should have said here that when we do the complex conjugation, of course one understands here that d mu acts to the left. All of these derivatives act on the psi to the left, where normally derivatives are acting on what comes after them, but nothing comes after them to the right here. It is understood that there's a derivative d mu acting on psi, and when we take the complex conjugation of that, it's still the derivative of psi. We just write it in this form. Good. So the interpretation here of this equation is that the field psi bar represents an antiparticle instead of a particle. That is just a Hermitian conjugation multiplied by gamma 0, but that means that it represents the antiparticle because that the zero momentum energy is suddenly minus m. Now, we investigated in the last lecture the plane wave solutions to the normal Dirac equation. And we wrote those as the positive energy solution of spin r is equal to u r of momentum p e to the minus I px, with u r of p equal to square root e plus m, just a normalization factor, and psi r for the first two components in the 4 spinner, and sigma dot p divided by e plus m psi r for the lower two components. Here, psi 1 is just 1, 0, and psi 2 is 0, 1. Spin up and spin down. We also found negative energy solutions of spin r, 1, 2, up, down, and wrote those as v r of p e to the I plus x, not minus, where v r of p was again square root e plus m sigma dot p divided by e plus m phi r and phi r. So the complicated sigma dot p e plus m relates to the bottom bit for the particle spinner and the top bit for the antiparticle spinner. Here again, phi 1 is spin up, phi 2 is down. Now, by construction, the spinners U and V satisfy their respective Dirac equation in momentum space. And by that I mean that P slash minus M on U is equal to 0 and P slash plus M V on P is equal to 0. They also satisfy a number of relations which will prove very useful in calculations of scattering amplitudes. Now, firstly, they're orthonormal. By that I mean they're normalized and orthogonal. So U, V, orthonormal. So U bar R of P, US P. So remembering U bar is a row vector, the unbarred are column vectors. So U bar R US with the same momentum is equal to 2m, but only when the spinners have the same spin, which is true also for minus V bar R P Vs of P. Similarly, U bar R of P Vs, so if you take an antiparticle and the U bar of a particle and the spinner of an antiparticle, you get 0, and the same is true for minus here, the bar version of the antiparticle and USP. So these are some very useful relations that will help us in calculating scattering cross-sections, but they're the useful relations for the inner product, so to say, where you take a row spinner with a column spinner and get a single number out. One can also take the outer products that means take two vectors, column vectors, row vector, and make matrices out of them by forming outer products. And for those constructs, one finds that the sum over spins r equals 1, 2 for the column spinner, UR of momentum P, U bar of momentum P is equal to P slash plus M. And one also finds that the sum over spins of V of momentum P, V bar of momentum P is equal to P slash minus M. The signs are the opposite of what enters in the Dirac equation for the spinners. We will now consider the Lorentz transformation of solutions to the Dirac equation. So, Lorentz transformations of spinors. So let's first consider the Lorentz transformation of the Dirac equation itself. So what we will find, or what we will seek to find, is if we've got a spinor, how will that Lorentz transform? And we'll postulate that it will transform linearly, which is not a crazy suggestion given that the Lorentz transformation itself is a linear transformation. So we'll postulate that psi of x on the Lorentz transformation will go into another spinor, psi prime of x prime, where x prime is the Lorentz transformed position, which will be equal to psi prime, obviously, of lambda x of the Lorentz transformed x. We'll say that that should be equal to a matrix operating on the spinor indices as a function of the Lorentz transformation matrix times psi of x. Now, this of course means that psi bar, which is gamma naught psi Hermitian conjugated of x, will go into psi bar of x prime, which is equal to psi bar of x gamma naught is Hermitian conjugated lambda gamma naught, because gamma naught squared is 1, where S of lambda is a suitable 4x4 matrix operating in spinor space. So it operates on the spinor indices of the column vector psi. Now let's look at some of the properties that this S must fulfill. So if we look at the Dirac equation, the Lorentz transformed Dirac equation, that will obviously say that I gamma mu d bar mu minus m acting on psi prime of x prime, and what we want is that the Dirac equation is Lorentz invariant. Good, so we say, well, we know what this is. This must be equal to, and then we just put in, we know how the d mu transforms. So we get I gamma mu let's write this differently. So we know how the d mu transforms. That will be lambda inverse mu d nu gamma mu minus m. And we already know how psi prime, that's the postulate, that will transform as an S. Now, when I say that we want the Dirac equation to be Lorentz invariant, that means that if psi here is a solution to the Dirac equation in the coordinate system that we start from, and we transform psi to psi prime with the matrix S, when we go from x to x prime, then if psi is a solution in the unprimed coordinate system, then psi prime will be a solution to the Dirac equation in the primed coordinate system. And then we need to understand what properties that requires of S? Well, let's have an inspired guess. Let's say that, right, so what we need is that we can take S onto the other side, and then we have the Dirac equation d gamma minus m on psi. So we need to have special properties of S when we commute that to the other side of the equation here. So let's guess that we have gamma mu S of lambda, that's what we have now, gamma mu and a S. And if that turns out to be equal to, we want it on the right, on the left, sorry, such that we can apply the Dirac equation to psi. If we have that equal to S lambda mu rho gamma rho, then the Dirac equation, then and only then will the Dirac equation be Lorentz invariant. Good, so let's see what this gives us. This gives us that I d prime mu gamma mu minus m psi prime of x prime is equal to, we have the equation up here, we use here the gamma mu, gamma mu and the s, we write instead as s capital lambda mu rho gamma rho, so we get that it was equal to, let's write first here, we have then a s of lambda, and then we have a I, we have the lambda minus 1 mu, then we got the lambda mu rho, we have the d nu, and we have the gamma rho minus m, all acting on psi, on x. But lambda inverse mu, this should be mu up here. Lambda inverse lambda mu contracted like this is nothing but g mu rho. So what we have here is s of lambda, and then we have I d nu gamma nu minus n psi of x. Now, if psi is a solution to the Dirac equation in the unprime coordinate system, then this is 0. And that means that if psi is a solution to the Dirac equation in, I was going to write S, the coordinate system S, then psi prime of x prime equals S of lambda acting on psi is a solution in S prime, because this is the Dirac equation in the prime coordinate system and it's equal to 0. So therefore psi prime solves the Dirac equation in the prime coordinate system. That's really good. We've now understood how solutions to the Dirac equation transform during a Lorentz transformation. We haven't quite derived representations of S, but we have a property of S in that gamma mu S lambda is equal to S lambda, and then the Lorentz transformation matrix lambda mu rho gamma rho. I should say, of course, that lambda mu rho is the Lorentz transformation that takes x mu into x prime mu which is lambda mu rho x rho under Lorentz transformation. Good. Actually, that equation for S that we have up here is enough to construct S, but we won't need explicit constructions of it. We'll just need this property that is necessary for the Dirac equation to be fulfilled, to be Lorentz covariant, to be fulfilled in both S and S prime when psi prime is found by having S acting on psi. So by direct observation, one sees that if S Hermitian conjugated on lambda is equal to gamma naught is inverse of lambda gamma naught, then we also have that psi prime of x prime, which is of course the prime of S of lambda acting on psi of x. So that will be equal to gamma naught so we have here psi prime is of course psi prime dagger gamma naught. That's how we define the bar, is the Hermitian conjugate and gamma naught. But psi prime Hermitian conjugated is equal to S psi Hermitian conjugated. We still have the gamma naught. And this here, the Hermitian conjugate of two matrices, will be equal to psi Hermitian conjugate, S Hermitian conjugate, and then we still have the gamma naught. But of course, we can insert here two gamma naughts. We remember that gamma naught squared is equal to the identity 4 by 4. So if we insert gamma naught squared here, then we get that that's equal to psi Hermitian conjugated gamma naught, and then a gamma naught S dagger gamma naught. But this, of course, we can write as psi bar, and then S dagger or S minus 1 lambda, right? Because if we have gamma naught S Hermitian gamma naught, that also means that S inverse of lambda is equal to gamma naught S Hermitian conjugate of lambda gamma naught, again because gamma naught squared is equal to 1. Good. So we understand some properties of how the psi bar transforms. That has S on the right hand side of the row vector instead of having S acting on the column vector psi. We can use all this to understand how so-called bilinear products of psi and psi bar transform under Lorentz transformation. So, let's see here, Lorentz transformations. Bilinears. What do I mean? I mean, let's consider, because they arise very often when we deal with Feynman rules, let's consider constructs of the form psi bar times a matrix in spinor space. I said psi bar, a matrix psi, where gamma is 4x4 matrix in spinor space. So acting on the spinor indices of psi and psi bar. Now, let's consider all possible gammas. We want to show that gamma, whatever form it takes, can be decomposed into a set of bilinears, and bilinears, this is exactly a bilinear. It has two powers of psi, a psi bar and a psi, that's called a bilinear. So we want to show that for any matrix gamma, it can be decomposed into a set of bilinears. This psi bar gamma psi can be decomposed into a set of bilinears, which each have a definite transformation property under the Lorentz group. So no matter what gamma is, we can decompose it into psi bar, some gamma mu for example, psi, some other gamma mu's, and each of these decompositions will have specific properties under transformations by the Lorentz group. So a vector, axial vector, etc. So since gamma is a 4x4, we expect that we'll need 16 different bilinears to describe all possible gammas. Now let's see some that we already know. So for example, the construct psi bar psi, how will that translate on the Lorentz transformation? Well, a Lorentz transformation sends psi bar, we just did that, psi bar goes into psi bar S inverse. So this one here goes into psi bar S inverse. Psi goes into S psi. So of course S inverse and S is just the identity. So we get here psi bar psi. Maybe this wasn't clear enough. I'll just do this again. So psi bar of x, psi of x under Lorentz transformation goes into psi bar prime of x prime, psi prime of x prime, but this of course is equal to what I wrote here. So that's what I meant with goes into. When we do a Lorentz transformation, it translates into psi bar of x, psi bar prime of x prime, psi prime of x prime, which is written up here. Good. So the product psi bar psi is invariant. It's the same in both frames. So it's invariant, it's a scalar. Let's see what happens with psi bar gamma mu psi. Now, under a Lorentz transformation, this of course goes into psi bar prime x prime gamma mu psi prime of x prime. But this is equal to psi bar S inverse lambda, gamma mu, and then S of lambda psi of x. Good. But if you use the property that we just used to define this up here, then in gamma S is S lambda rho. Okay? So when we down here have a gamma S, we just replace that by S lambda. Right, so our gamma S we replace by S and then a Lorentz transformation and the gamma rho. So this is equal to down here psi bar, space psi bar, the S will cancel with the S bar, we get a gamma rho, and we have a psi. Now, what did I do with the lambda mu rho that I should have written? Well, the lambda mu rho is a 4x4 matrix that acts on the Lorentz indices, not the spinor indices. So the lambda should have been in here if I used the formula up there. But actually, it lives in a completely different space, so I might as well write it out here. I can also say I use the index notation where I can move everything around, because they are just numbers. For each mu and rho, they are just numbers. So lambda mu rho, psi rho. So this here is how we would expect a vector. This describes exactly the Lorentz transformation properties of a vector. So when we go from the S to S prime coordinate system, psi bar gamma mu psi translates exactly like a vector does under the influence of lambda mu rho. So this is a vector transformation. So psi bar gamma mu psi is actually a vector. Good. So we constructed the scalar and 4 for mu equals 1, 2, 3 quantities now. We could construct some more. We need a 16. And we could construct another 6 quantities by considering what we call sigma mu nu, which is the normalization of the commutator between gamma mu and gamma nu. Now, the reason that these are chosen like this is that they arise frequently when we consider Feynman rules. Good. We note here the product gamma mu, gamma nu is not linearly independent from all other matrices, because of the Clifford algebra that says that gamma mu comma gamma nu is equal to 2 g mu nu, and then the identity matrix in spinor space. Anyway, what we find is that psi bar sigma mu nu psi under Lorentz transformation will go into psi bar S inverse lambda, then I over 4 gamma mu gamma nu S lambda psi. But we already knew what happened every time we have an S and a gamma mu, we get a lambda mu rho and a gamma rho, right? Every time we commute a gamma mu with the S, we get a capital lambda mu. We have to do that twice here. We get one for the commute for moving it through the gamma mu and one for moving it through the gamma nu. So what we get here is equal to lambda mu rho lambda nu sigma psi bar sigma rho sigma psi. Right? This is exactly the transformation properties of a tensor. Right? It's a construct with two Lorentz indices, and it transforms using two Lorentz transformation matrices, lambdas, one acting on each index. That's the definition of a rank 2 tensor. Now, the reason that we only had 6 and not 4 by 4 is that the gamma mu's are not linearly independent, right? So we only get 6 extra. Now, in addition to the 4 gamma matrices, there's another matrix construct that appears often, and we would like to parameterize our 4 by 4 matrices and their transformation properties in terms of this new matrix that's called gamma 5. So gamma 5 is defined as I and then the product of all the 4 gamma matrices that enter the Dirac equation. Oops, 3. Which can also be written, turns out, as I over 4 factorial, and then the totally anti-symmetric Leibniz beta symbol, gamma mu, gamma nu, gamma rho, gamma sigma. Which is a complicated way of writing 0, 1, 1, 0 in this representation. Now, this satisfies that gamma 5 squared is equal to the identity matrix, and also that the anti-commutator between gamma 5 and any of the 4 other gamma matrices is 0. And also that gamma 5 Hermitian conjugate, obviously, is equal to gamma 5. Good. Now the factor I here is to ensure that it's Hermitian, the Hermitian conjugation. Now, using this gamma 5, we can construct 5 more bilinears. So what we find, for example, is that psi bar gamma 5 psi goes to psi bar is inverse lambda. The gamma 5 is the I epsilon mu rho sigma. Then all the gamma mu rho sigma S lambda psi. And as before, every time we commute a S, this S here, through all the gamma matrices, we get a Lorentz transformation matrix lambda mu. So, and the I epsilon, that's just a number, we can take that out of the spinor multiplications because it's only dependent on the Lorentz indices. So it's I epsilon mu nu rho sigma lambda mu alpha lambda mu beta lambda rho gamma and lambda sigma. Let's call this something else, delta. And then we get a psi bar gamma alpha beta gamma gamma and gamma delta on psi. Good. Now this thing here is actually the determinant of lambda. And then we have psi bar, then the determinant of alpha. Let's just here. Determinant of lambda psi bar. What we have here is just gamma 5 and psi. Now I'll just write this up. So what we have here is that psi bar gamma 5 psi translates into psi bar gamma 5 psi with the determinant of the Lorentz transformation. Now this is how a pseudoscalar transform finally, I'm not going to go through the details here, but psi bar gamma 5 gamma mu psi will go into determinant lambda, and then an extra lambda mu nu psi bar gamma 5 gamma nu psi, and that's exactly how a pseudo vector translates. There's an extra sign compared to how a vector translates, and here for the pseudoscalar it translates almost like a scalar. There's just the sign of the determinant in the Lorentz transformation. Good. So we've now found a set of 16 linearly independent matrices, and let's just write them down. There was the scalar gamma 5 gamma mu gamma 5 and sigma mu nu, which was defined as I over 4, commutator between gamma mu gamma nu. So it's that any bilinear such that any bilinear psi bar gamma psi can be written in terms of these matrices that have definite transformation properties under Lorentz transformations. So they transform either as a scalar, a pseudoscalar, a vector, a pseudovector, or a tensor. Good. So gamma 5 was useful in constructing these, perhaps because gamma 5 often appears, I said that gamma 5 often appears in the Feynman rules. Why is that? So gamma 5 appears in Feynman rules because that it is used in projection operators. So, for example, you can project to the left-handed states by multiplying by 1 minus gamma 5, and you can project on right-handed states by letting the matrix 1 plus gamma 5 act on the spinors. Now you can check explicitly these are projections. What do we mean that they're projections? We can check that p squared, if you project twice, it's the same as projecting once. And we can check that if we project first on the right-handed state and then project on the left-handed state, we get 0. Now when these projection operators act upon a Dirac spinor, they project out either the component with left-handed chirality, that's PL, or right-handed chirality, PR. These projections appear whenever we consider interactions that know left from right. So for example, every time we have anything with the weak interactions with the W bosons, then since they only couple to the left-handed particles, there will always be a PL projection. And that's why gamma 5, or that's one of the reasons why gamma 5 appears so frequently in the Feynman rules. Now, one has to take a little bit care when defining the handedness of antiparticles, because if we have a psi bar left, then that's obviously equal to psi Hermitian conjugate gamma naught, which is if we had left, then psi bar left here, so that's equal to psi Hermitian conjugate PL gamma naught, because that psi Hermitian conjugate left is the left-handed psi Hermitian conjugated, and the left-handed psi is PL psi, and therefore when you take the Hermitian conjugation of PL psi, we get psi Hermitian conjugate PL gamma naught. So that here is equal to psi Hermitian conjugate gamma naught PL goes through, when gamma naught goes through gamma 5, you change sign. When gamma 5 term here changes sign because gamma naught is commuted through, the P left becomes a P right. So that here is equal to psi bar P right. So a left-handed antiparticle that we have here appears with a PR operator next to it, and a right-handed antiparticle appears with a P left. But that's because that the operator doesn't act on the PL to the left, but sits on the right side of it. And the gamma naught changes the sign on the gamma 5 term.